And so today I'm going to be talking about mostly about the Navier Systems Engineering Transformation. That was that's first sponsor, and but we also have another sponsor. I have one slide that I actually have from my other sponsor. Okay, and so first off, I want to say that we're going to talk about some tools here that doesn't necessarily represent the endorsement by our university or our sponsors. That was the lack of endorsement. And so the other thing too is that systems engineering is a team sport. And so we've been actually doing this since about 2013, which I'll hit on in a minute. But there's a lot of collaborators. So even though I'm up here today, there's been a lot of people who have actually contributed to both the work of the Army and the Navy. And so I'll go back again, starting with Mr. Dave Cohen. He basically said that the way that Navier was actually getting through programs was taking too long. And so he wanted to consider using digital models. And so we did a global scan starting in 2013 and visited 30 different organizations, 21 on site all day long. And that was with also the person that took over, Mr. Hammerguro, and they brought the best and the brightest and told us about the best stories as we asked them, tell us about the most advanced holistic approach to model-based systems engineering, model-centric engineering, model-based enterprise. We listened to it all. And at the end of 2015, the Navier leadership decided that they have to transform, not just evolve, to keep pace with something that appears to be accelerating in the fact of model-centric engineering is what was the term that they actually used. And so Dave Cohen came up with this concept that's more of an iterative kind of an approach where he said he's going to blow up the actual proverbial V model. And so that's a little bit of what we're going to talk about here today is we created this surrogate pilot, and Mr. Cohen actually had Altair, a company that was working in the automotive industry, because he felt that they would actually go potentially faster than some of the folks that were in the DoD space. And so I'm going to first talk a little bit about some of the lessons learned that we have, and we're correlating this to some digital engineering measures that were produced by another CircRT. And then I'm going to really just step through the surrogate pilot model. And what we decided to do very early on was to demonstrate the art of the possible and model everything. Not that anybody would necessarily do that, but in doing so, we end up finding out that we eliminated some things that were traditionally done, or they became subsumed within doing the model. And so I'm going to give an example and talk about what an authoritative source of truth is versus a single source of truth. I'm going to talk about the full stack of models, and we produced 23 models, and I'm going to show you probably ones that are about 14 of the different models that we've actually used. So this is not a plan. This is actually, it's done. We've actually made these things. So that include things such as graphical ConOps, which we have used the Unity gaming engine for doing visualizations. We've built mission models, system models, multi-physics models, and we've even hooked to an information model that's based on the concept of an ontology that actually align with, say, reference architectures. And I'll give a few other different definitions of these things to make it clear as we go through here. And then there's we also link the technical data, which is in the full stack, with the stakeholder analysis model. And one of those is the cost model that I'm talking about. And again, if you visit a table out there, Taylor will be able to take you through some of the use cases for the cost model. Then another thing that's very important is we actually have transformed from using just processes to actually modeling methodologies where we actually produce specific types of artifacts. And when we do that, those artifacts can be used as information evidence about digital sign-offs. And so that is the way that, again, Mr. Cohen wanted to eliminate C drills, which is the contract data requirements list. But we actually talked about how we could actually do some transformation. And so all of this is also now provided in terms of workforce development training and materials. So that's actually a big plus because engineers and others tend to learn a lot from examples. So when we started this pilot, which was late 2017, was just after the hurricane in Puerto Rico. So we started with a search and rescue mission, and Dave Cohen also was very concerned about doing a lot of stuff on the proverbial left hand side of the V. And so he created some constraints that would be related to flying fast and flying far. So it eliminated a traditional helicopter as a solution. We end up with this tilt rotor, which is like the Bell Eagle Eye. And that's actually out there in the NavAir Museum. And so the first thing we did was also look at multi-physics kinds of design. So I'll talk a little bit about that one. The next one, use case we talked about was airworthiness. How do you get a flight clearance? And so that brought in the interaction between the other capabilities, which is the launch and recovery system, as well as the Bell Eagle Eye. And then the next thing that Himagura thought would be necessary is to develop cost models. And so there was a model-based systems engineering effort to build cost models, and we actually developed a deep dive to the cost model. And he felt that was important because programs would need cost modeling to actually move out. So now what I did, and this was done for another CircuitRT 1001, Tom McDermott asked me, well, Mark, do you think you could actually look at the lessons learned and actually do a mapping to these digital engineering success criteria measures? And so I looked at the tops, or I did it against the 17, and then they rated them here. And so some of the things that that percolated to the top is establish the infrastructure for your digital engineering environment and your authoritative source of truth very early on. We found that it was definitely technically feasible to model everything. And again, as I said, some things seem to be subsumed into the model. It was really important to come up with modeling methodologies as opposed to just processes, because that provide the basis for doing digital sign-offs. And I'll give some examples on that one. And because we talked to a lot of the industry about it, there was a lot of buy-in, and we got some RFI responses that they would be willing to actually participate and actually operate in a very different kind of way. So it was a new operational paradigm. And so some of the things that actually occurred are improved traceability, improved consistency, improved, collaboration, and a lot of things really related to access of information. So from here, we also have this digital engineering roadmaps that we've been actually putting together, and I like to use this as an example to tell the story. So for all of you that might remember the strategy, which is decision making, authoritative source of truth, tech and innovation, collaboration, and workforce development, these are the prongs that actually lead towards a more advanced state. And so these are all going on in parallel. So given the current state, it's being here. Model-based systems engineering and specific things like the system modeling language have been around and actually been standardized since like 2016. So it was a tech innovation that we actually brought in, but we actually coupled that with quite a number of other things. So another one was NASA JPL provided this open model-based engineering environment, which actually we used to establish an authoritative source of truth using a collaborative approach. We again transform beyond processes to create methods, and those methodology artifacts are used for enablers for digital engineering. In our Army work, we've also pulled in the use of what's called semantic technologies and ontologies to formalize information across multiple domains, so we can reason across domains and up and down the different levels of abstraction. And so the semantic integrity provides a basis also for doing things like artificial intelligence and machine learning on formalized information. And then we had another task that we looked at that mapping to the digital twin, which I'm not going to talk about today. So I've sort of just articulated these specific words here, but here is some notion of different levels of abstraction, and at each one of these kind of levels, there's different kinds of methods that should actually apply. And so, but how model-based engineering strengthens systems engineering is because it not only just represents the requirements. And when I first started with NavAir, all they talked about was these textual requirement documents that had a bunch of shells in there. But with model-based systems engineering, we can actually capture the structural analysis, behavioral analysis, interfaces that actually lead to new sets of requirements. And they can characterize those at different levels of abstraction, mission, system, subsystem. And we're also able to leverage technology automatically, or for DocGen, using DocGen, which is part of OpenMB, to generate stakeholder relevant views in documents, but also in a web browser that can be navigated. And so therefore, we're not trying to force stakeholders to navigate these models. Now with that, and if we represent the information in an authoritative source of truth, and we actually provide information access to that, then we can actually do visualizations to support decision-making, goal number one. And again, all of this is done with unclassified examples that are being used and transformed into workforce development. All right, so this is just another representation of the different views. These top level views may be more associated with model-based systems engineering. So you have the operational information, but you have one or more capabilities at the mission level. And this particular boundary right here is the initial system model, which is typically where, say, a Navigator would stop, because it describes things in terms of the logic and the functions that should be applied from a system model point of view. And usually the contractors pick up afterwards. So they actually will complete the model, but will make particular decisions like physical kinds of decisions. Like if we said that we needed a landing gear, they might decide, well, we're going to pick out electrical versus a hydraulic. And then that continues to be decomposed down through the component levels. And this is more typically referred to as model-based engineering, because it has the discipline-specific kinds of things. And so it's, therefore, systems engineering is a thing that actually pulls information together across all these discipline-specific types of things up and down the full stack. All right, so now let me start with another example diagram, and just pay attention to like the words, not so much the icon, because what I'm trying to explain is model-based systems engineering produces artifacts that go beyond just the requirements. Okay, so typically when you come from one level to the next, let's just say the mission level, we could have formalized these in SysML, using the system modeling language, as requirement blocks. Okay, the other thing that usually comes from the upper level is a set of use cases. All right, so now we start the analysis process. So we can do behavioral or structural analysis, look at the blocks, the parts, and their properties, such as weight and other things. We can also look at the interfaces between the parts, but then we could also have refine the use cases in terms of behavioral information that describes control flow as well as data flow, which could also be used to inform us about the interfaces. We can refine use cases, say in sequence diagrams, which is related more to communication systems or software. We can also refine use cases in terms of state machines, such as take the UAV out of the hangar, set it up for takeoff, fly around to its mission, land, go to maintenance, back to the hangar. And then we can also describe abilities, such as hazard analysis that might go on. Lastly, another way to actually further define constraints, and this will be used in the cost modeling. If you, again, go look at the demo that I'll talk about later, we can define constraints related to these value properties. And while there are simulators that can occur here, this is where we begin to link to the actual multi-physics kind of design. So the scenario is that suppose that we wanted to have a cruise speed of 180 knots, but when they actually did analysis with, say, this is computational fluid dynamics, the aerodynamics over the frame, they may actually determine that, oh, when they have the hydraulic landing gear, which is necessary, that the weight becomes too high, and so therefore the maximum value that you could have is maybe only 170 knots. So that's how the multi-physics on the left side of the V can be informing us, because we're having much more sets of rich kind of calibrated modeling and simulation kind of capabilities to actually take that value property and map it back up to the actual mission model. But also that particular value property is going to be used in the next set of shell statements, which I'll talk about in a second. Also, we have all this behavioral information that is also now prepared for us ahead of time, even before we maybe even issue an RFP. Now we actually can actually create the next level set of requirements. And again, being informed by the things like our multi-physics analysis, we can now say that the UAV needs to actually have a cruise speed of 170 knots, or it might need to have an endurance of 50 hours with a threshold of 2. And then we can actually trace that information from the new set of requirements back to the mission level requirements. So these are all the artifacts that can be actually provided to a contractor at RFP, not just the shell statements. So when they are looking at the requirements and they find something that's in question, they can actually understand the association from the various either behavioral or structural information that was created. So putting all of that as part of the contract, as part of the government furnished information with the generated spec, could actually help us have fewer issues going forward, where they actually, the contractor may have to remodel the requirements, which I do know has been done by organizations. All right, so given that, what is an authoritative source of truth? Okay, so here is our full stack of models, and an important capability as an enabling characteristics is this mechanism called the project uses. It's like a model import. So what this means is that the launch and recovery system imports the mission model, just as the Skyzer actually imports the system model, and the contractor model imports the Skyzer model, which imports the mission model. So let's just assume that we have some kind of a change that's necessary in the launch recovery system, and that actually changes a constraint in the mission model. Now that's all visible down through the actual full stack of models, and we can actually talk about that in a minute. So the other thing that they did with NavAir is they came up with this NavAir systems engineering method. It goes, again, it's more than just process models, which is the what. It actually describes the specific artifacts, which is the how, like I just pointed out a minute ago. So these models are built using that basic standard, so they're compliant with that model. So this is a type of a reference model for processes, okay? There's other kind of reference models that are supersets of other things, such as military standards, say for airworthiness, which is based off of, say, a MIL standard 516C, or cost modeling, MIL standard 881E. And so the next thing we did was we described how to take specific subsets of these reference models and actually link those to the actual technical data, okay? So that included airworthiness. So for this specific case here, we're not actually taking the entire airworthiness model, we're just creating an instance that provides the criteria that's related to what's in the technical stack of data. And then we did that also for cost modeling. So let's go back to my example again. So now we can actually say that, oh, we can actually see that going from that particular change, maybe they decided that with the air vehicle needing to be able to come down to 25 feet per second, they needed a hydraulic landing gear. Well, that might have cost us to say that, well, we need an additional type of airworthiness verification criteria, which means that we also needed an additional kind of a test. And so now, because we've actually linked not only the technical data, but we've also linked airworthiness and testing information, we can actually assess the cost. And so when I was at the first ERIC event, and some of the people from the acquisition side said the biggest problem was that when they have all these documents and they're all really related to one another, it's very difficult for them to support decision making. This is exactly the reason why we want this authoritative source of truth, so that we can actually see the actual kinds of things that can actually affect everything, right down to, say, cost modeling. And again, the tutorial on Thursday is going to bring in our subject matter expert who helped us develop all this cost modeling, Mr. Don Allen. And so that's from 9 to 11 on Thursday. Lastly, we also created what's called cost constraints. So cost constraints are used for the different models. We created a couple of different kinds and showed additional kinds of automation. So what they would provide, say, to a surrogate contractor, or our contractor, would be surrogate equations. So in other words, they would show them the different cost equations that are related to the work breakdown structure that came from MIL standard 881E. But when we actually do source selection, you might pick a particular contractor, and NavAir has kept track of the actual variations in the different cost equations for different contractors over time. We showed and created a demonstration to show how that can be switched out. And again, Taylor can actually do that out in the hallway, and we will also have it as part of the demo on Thursday. Finally, the last kind of reference model, sometimes referred to as reference architectures, are generalizations of prior designs. So a lot of times if we're going to start a new UAV, we can go to a reference architecture, which might actually provide us a starting point for some new UAV. It might be a 60% solution. And I also want to point out that we're really interested in keeping reference architectures, not just for systems, but also for various different kind of mission types, because that exists too. And I mean, that follows up on one of the earlier talks that was given today about knowing and keeping track of the different patterns that might be applied at the mission level. All right, so that was the full stack of models. Again, we have 23 models that we created over the period of about 3.5 years. But here's the digital engineering environment or integrated modeling environment that we had set up. So we had the government side, which used the NoMagic products. This is a system authoring tool, plus its repository called the Teamwork Cloud. But we also use the OpenMB information for our model management and also the view editor, which actually worked with DocGen. So this is what we had on the government side, and the surrogate contractor had it set up the same way. We had one at Stevens too. So let's go back to our scenario. So suppose that the contractor says, oh, under certain weight and weather conditions, that the endurance of 50 hours with a threshold of 2 is not achievable. And they can actually go back up to the view editor if they have the appropriate things, go directly to the threshold value, put a hyperlink into their analysis, and now the subject matter expert from the Navy could actually hyperlink into the environment. We created a video showing how this is possible, and actually look at the detailed analysis in the contractor's model, because the government is not going to replicate all the different kinds of tooling and environments. They're going to need to work and ask for in the contract the ability to actually access information in the contractor's part of the authoritative source of truth, because you can see here. And so then the subject matter can see that data, go to the specific value in the view editor, create a branch, part of configuration management, change the value, see if they can get a digital sign off. If they can merge the value back into the master branch, the trunk, and then commit commit the information back to the Teamwork Cloud. And again, that's another scenario that Taylor will actually show you tomorrow. Now, this is not a hierarchy. This is a graph like the internet. So let's give another scenario. So suppose this is the Joint Strike Fighter, and this is Lockheed Martin. So they actually do part of it. But so the government has a relationship with Lockheed, but the government would also have a relationship, say, with Rockwell, who actually produces the helmet. But also Rockwell and Lockheed would have a relationship. This is the whole networked idea of a graph-oriented structure for the authoritative source of truth. And these are the kinds of tools that would actually be used for accessing that kind of information. All right, so now let me move on to the OpenMB capability. This one we selected very early on because they actually had a model management system. And why this got created by NASA JPL originally was for that exact scenario that I talked about. The old traditional model management, which was file-based, would not allow someone to just manage just the individual change of that value, like threshold value. So in here, you can manage down to the individual object level. But they also created this notion of a view and viewpoint hierarchy, which I'm going to show you in a minute, because they realized that there's going to be a lot of subject matter experts that will never navigate or use a system authoring client. All right, so this is what we produced it with it. I'll talk about that in a minute. But so this particular set of steps right here, this is the process model that NavAir came up with. So they have processes for doing mission models, system models at the black box, at the functional logical level. And we also created the RFP response, the contractor. We simulated creating that with a more detailed set of information. So all these have models that actually are compliant with NAVSEM. And so what they also did is that they said, not just they're going to have a process guidance, they're going to actually talk about specific kinds of artifacts that need to be produced for each of these steps. And with that, we were then able to create the notion of a digital sign-off. Okay, and I'll go into that in a minute. So how does this work? Well, the DocGen, it has a view. Okay, so as a document, there's a view. And then the subject matter expert can actually expose the actual model object. And then they would use a viewpoint, which is actually like a little program that can grab out information such as tables out of here and actually place that information at the particular views. And so one of those turns out to be the digital sign-off. And so here is an image of that view, okay, so here's what's called the selected operational use case. And we added the digital sign-off where if you had access, you can enable edits in a view editor, a web browser, and then be able to set approvals. Okay, sign-offs, you can have they're template-based. You could even say, what the percentage complete is, like, or what risk it is. So some of that is still under development, or we need to actually have more conversations about it. Here's yet another one related to, say, fault tree analysis. This is how we would do hazard analysis, for example, directly in the model again. And I use this for an additional point. So here's a fault tree. This is like a hazard analysis that could be used for cyber or for safety kinds of things. But this is an and/or tree, and at the bottom here is what's called a basic event. And why I like to actually have requirements in the model is because what happens is if a basic event manifests, it means that the hazard could actually lead to a mishap. So what you want to do is you want to make sure that you create mitigation requirements to, in some ways, try to avoid actually having the basic event manifest in a hazard. And so this particular case it shows exactly why a lot of the requirements are not derived from upper level requirements. They're derived from the analysis. And by providing the analysis with the requirements, when we actually provide it to a contractor, gives them much deeper insight into the information that was used to construct these shell statements. Okay, so in this particular case, we're going to say that the digital sign-off was rejected because the reviewer thought there should be another basic event over here. So while it might have been, say, 75% complete, and it actually mapped information. So this just shows the template-oriented approach of being able to map the information to the traditional risk cube. They actually rejected it. All right. So now this was another thing that we did from an automation point of view. Some of these subject matter experts from Manor said, well, what happens if you do a digital sign-off and then the artifact, the diagram, changes? Well, we were able to show that we can detect that automatically and computationally change the value if it was accepted back to TBD or something of that nature, or give the actual approver some warning. But in this particular case, this provides another example of one of the things that Dave Cohen used to talk about. He wanted to be able to do more asynchronous and continuous reviews to actually assess a maturing design. So if we had actually had it rejected and someone came up and they added the case, we could automatically know that it would be time to come back and revisit our digital sign-off again. And so that was achieving something. It was a slogan Dave Cohen used, which was a design review a day. The last thing that we did was there's a section called the infamous section L that is part of a normal RFP. And one thing we showed is to take that section L and have it embedded in the RFP response from the contractor. And then we had our subject matter expert go down through, and Don Polakich, he had not ever used a system authoring tool, nor did he even take it, but he was able to read these models. And that's what we're trying to get here with the acquisition people. They're not going to have to build these models. They just need to be able to read the models. Okay, so he went through the entire source selection of technical evaluation and actually provided a review directly within the model. So those are the kinds of things we can do. And we're just barely touching on some of these kinds of things. So there is still more to do in terms of looking at different kind of templates. But the other thing too is that I think that there was a recommendation by another gentleman, a subject matter expert from Navier, Greg Page, who came up with this idea that we could actually do continuous kind of reviews and actually come up with a baseline progress measures based on, now that we actually have the real measures and metrics that are captured automatically. And so we could judge a maturing design versus having these monolithic kinds of reviews that we had traditionally done. And so there's a video on that if you'd like to actually see how the digital sign-offs are done. So this is our final slide, and this is a distro A slide that I can actually put up for our Army work at DevCon. So they also have a full stack of models. The thing that's very different about them is that they have to go the full stack all the way down to the discipline specific information, because they tend to build prototypes of these kinds of things. So they have reference architectures, and we've been able to create some ontologies for those that we use to reason across information. And so we have mission models. We actually have graphical concepts with the Unity gaming engine, as we talked about. We have system models, and we have analysis models. And then down at the bottom here, we end up having all this discipline-specific stuff. And the ontologies really help by allowing us to create, we have this repository. It's referred to as the interoperability and integration framework. And the idea is that with today's technology, we can probably have interoperability and get and have cross-domain information pulled together in a single place. So therefore, we could reason about, say, the computational fluid dynamics, the aerodynamics of it, along with the finite element analysis, the structural kinds of stuff, but also potentially to understand the 6 degrees of freedom in terms of its flight trajectory that could also be reprojected in, say, graphical concepts, which we have done. So this provides a much more rigorous way to bring metadata from these higher fidelity simulations back into the system model and mapping them all the way up to, say, for example, key performance parameters that are in the mission level. Again, being able to go up and down the proverbial left side of the V, doing analysis with multi-physics and high fidelity models, all on the proverbial left side of the V, to come up with better requirements, but also to actually still provide those models so that they can go to the contractor as additional pieces of information beyond just requirements. All right, and then again, we did use the view editor in digital science. And so we've captured all this. There's more than 60 products, and there's a spreadsheet out there on the All Partners Network. So there's a lot of videos, but there's all the models, reports, and many other kinds of things. You can actually sign into that. There's 2 different groups. The research group has stuff that might be more distro D kinds of things, but yeah, it's all available if you're interested. And with that, I thank you, and I hope you get a chance during the break tonight to actually go over and visit Taylor to hear a little bit about some of the stuff that we've done. He can show you around. Thank you.
Hey, Mark, can you talk a little bit about the learning curve that the government people had, working in this environment, and some things you did to overcome that?
Yeah, so in terms of learning curve, the one thing that the government did do, and this is more NavAir, is they created different levels of training that they did. So they recognize some of the things that would be, let's see here. I'll go start my video. Okay, all right, all right, there you go. Yeah, so they ended up created different layers, and you can actually get that too. The person that can actually provide you the different kinds of things that they have is, her name is Maureen Nardo, Dr. Maureen Nardo. But for the engineer types, they also used a lot of the Georgia Tech training, including the one that actually was one of our PIs, Dr. Russell Peak, who's been on our task for quite a number of years. And that's the way that they started it. And then what they did is that they moved towards creating more organic kind of training. And so there's a lot of lightweight training that was done, and it's provided. You can get it. Any services can get it. Maureen Nardo does it every month. And so hopefully that's a good enough answer for you, Tom.
Another question. Can you recap which tools were custom versus commercially available?
Pretty much all the tools that NavAir uses are all commercially available. And the Army also has us using all commercially available tools. I mean, we use the open source OpenMB. That was very good because it was actually ahead of the commercial products for being able to do things like the digital sign-off, for example. And then the DocGen also showed it was very valuable for subject matter experts just to look at a generated view, so they didn't have to navigate these SysML authoring tools. Other question?
Oh, thanks, Mark.